Could our universe, with its billions of galaxies, exist inside a black hole? This question, once purely theoretical, now drives cutting-edge research in astrophysics. To explore this idea, we need to understand what a black hole is and how our universe might mirror its structure. Let's break it down clearly and systematically. A black hole is a region where gravity is so strong that nothing escapes, not even light. It forms when a massive object, like a dying star, collapses into an incredibly dense point. This point, called the singularity, warps spacetime, the four-dimensional grid that defines how objects move and time flows. Picture spacetime as a network of coordinates, not a physical surface, twisted tightly around the singularity by its immense mass. The boundary of a black hole is known as the event horizon. This invisible sphere marks the point where gravity becomes absolute. Anything crossing it, from a starship to a beam of light, is drawn inward with no chance of return. The event horizon's size depends on the black hole's mass. For example, a black hole with 10 times the mass of another has an event horizon 10 times larger, as calculated by the Schwarzschild radius formula. Now, let's look at our universe. It has its own boundary, called the cosmic horizon. This is the farthest distance from which light can reach us, given the universe's age of about 13.8 billion years. Light travels at 299,792,548 meters per second. Beyond the cosmic horizon, roughly 46.5 billion light-years away, light hasn't had time to arrive due to the universe's expansion. Here's the key connection. The observable universe contains an estimated 1.5 times 10 to the 53rd power kilograms of mass, including stars, planets, gas, and dark matter. If this mass were compressed into a black hole, its event horizon would span about 46.5 billion light-years, nearly matching the cosmic horizon's size. The universe's average density, approximately 1 times 10 to the minus 27th power kilograms per cubic meter, also aligns with the density of a black hole of that scale. The match is not trivial. It suggests our universe's structure resembles a black hole's. The question is whether this is a coincidence or a clue to our origins. To investigate, we must delve deeper into black hole physics and examine evidence from our cosmos. This hypothesis, grounded in observation and mathematics, sets the stage for a profound scientific inquiry. The idea that our universe might exist inside a black hole hinges on advanced physics. Albert Einstein's theory of general relativity describes how mass and energy shape spacetime. Inside a black hole, this shaping becomes extreme. Past the event horizon, spacetime curves so tightly that it forms a new region, separate from the outside universe. This region acts like a distinct cosmos, with its own rules and structure. If our universe is inside a black hole, we could be living in this isolated spacetime. The event horizon would shield us from the external universe, making it impossible to see beyond. Our observable universe, defined by the cosmic horizon, might be the interior of this black hole. This model suggests our reality emerged from a black hole's core, a concept supported by mathematical solutions in general relativity. To understand this, consider how gravity works. It treats gravity not as a force, but as a curvature of spacetime. Massive objects, like stars, bend this grid,
causing nearby objects to follow curved paths. In a black hole, the curvature is so intense that all paths lead to the singularity, a point of infinite density. Beyond the event horizon, however, equations predict a new spacetime, potentially vast enough to house a universe like ours.
Recent research offers clues to test this hypothesis. Astronomers have studied the rotation of spiral galaxies, which resemble spinning pinwheels of stars. A study examined several hundred galaxies, using telescopes to observe their motion. The findings were unexpected. About 2 out of every 3 galaxies rotated in a direction opposite to our Milky Way galaxy. This pattern was seen in observations above and below the Milky Way's plane.
This rotational bias is significant. In a typical universe, galaxy spins should be random, with half rotating one way and half the other. A 2/3 preference suggests a coordinated motion across vast distances. This could indicate that the entire universe has a net rotation, a property described as angular momentum. Angular momentum measures how much an object spins and in what direction. Why do galaxies spin at all? When galaxies form, they start as clouds of gas and dust. As these clouds collapse under gravity, any small motion within them grows stronger. This is due to a law called conservation of angular momentum. A large, slowly moving cloud becomes a smaller, faster spinning galaxy. This explains why individual galaxies rotate, but a universe-wide rotational pattern is harder to explain. If the universe has a net rotation, it challenges standard models. The Big Bang theory assumes the universe expanded evenly in all directions, with no preferred spin. A rotating universe suggests a different origin, possibly tied to a black hole. This connection is intriguing, but requires more evidence to confirm. The discovery of a possible universe-wide rotation raises deep questions. In most cosmic models, the spins of galaxies should be random. Each galaxy forms from a collapsing gas cloud with its own unique motion. These motions, driven by turbulence, typically cancel out across the universe. A net rotation, where galaxies prefer one spin direction, suggests an unexpected order. This finding challenges our understanding of the universe's origin. Angular momentum is the key concept here. It describes how much an object rotates and in what direction. For example, a spinning top has angular momentum, which keeps it upright. In the universe, every rotating object, from planets to galaxies, carries angular momentum. This property arises during formation. As a gas cloud shrinks, its rotation speeds up, much like a dancer pulling in their arms to spin faster. This is called conservation of angular momentum.
In a typical universe, the angular momentum of galaxies should balance out. Half should spin one way, half the other, with no overall preference. The recent study of several hundred spiral galaxies found otherwise. About 2 out of every 3 galaxies rotated opposite to the Milky Way galaxy. This bias, observed across vast distances, hints at a universe with net angular momentum. Such a pattern is not expected in standard models like the Big Bang, which assumes uniform expansion in all directions. This rotational bias connects to the black hole hypothesis. Black holes preserve only 2 properties from the matter they consume: mass and angular momentum. When matter falls into a black hole, its rotational motion contributes to the black hole's spin. A black hole with significant spin
carries a net angular momentum, which could influence the space-time inside it. If our universe formed within a rotating black hole, it might inherit this spin, causing galaxies to align in their rotation. The idea is compelling, but complex. In a rotating black hole, described by the Kerr solution in general relativity, the internal space-time differs from a non-rotating one. The spin creates a dynamic environment, potentially shaping the universe within. The observed galactic rotation could be a remnant of this inherited angular momentum. The universe's mass, estimated at 1.5 times 10 to the 53rd power kilograms, and its density, about 1 times 10 to the minus 27th power kilograms per cubic meter, already align with a black hole's properties, strengthening this link. The evidence for cosmic rotation is preliminary. The study analyzed only a few hundred galaxies, a small fraction of the billions in the observable universe. Larger surveys, using advanced telescopes like the James Webb Telescope, are needed to confirm this trend. If the rotational bias holds, it could reshape cosmology. It would suggest our universe's origin involves a mechanism like a black hole that imparts coordinated motion across cosmic scales. This hypothesis remains speculative, but testable. Future research will measure galaxy spins across wider regions and refine our understanding of angular momentum in the cosmos. For now, the possibility that we live inside a spinning black hole offers a fascinating challenge to science, blending observation with bold theory.
The hypothesis that our universe exists inside a black hole relies on advanced theoretical models. General relativity, developed by Albert Einstein, provides the framework for these models. It describes gravity as the curvature of space-time, a four-dimensional grid of coordinates. In a black hole, this curvature becomes extreme, creating a region where normal physics breaks down. To understand how a universe could form inside, we need to explore specific black hole models, particularly those that account for rotation. Most discussions of black holes start with the Schwarzschild solution, which describes a non-rotating black hole. This model predicts a singularity at the center, surrounded by an event horizon. However, the universe's possible rotation, suggested by galactic spin patterns, points to a different model, the Kerr black hole. Named after physicist Roy Kerr, this solution describes a rotating black hole. Its spin alters the space-time structure, creating a more complex environment inside the event horizon. In a Kerr black hole, the singularity forms a ring, not a point, due to the rotational motion. This ring singularity is surrounded by a region called the ergosphere, where space-time is dragged along by the black hole's spin. Beyond the event horizon, general relativity predicts the possibility of a new space-time region. This region could be vast, potentially containing an entire universe. If our universe formed within a Kerr black hole, its net rotation could be a legacy of the black hole's spin, explaining the observed galactic alignment. Another key feature of our universe is its expansion. Observations show that galaxies are moving apart, with the distance between them increasing over time. This expansion, discovered by Edwin Hubble in the 1920s, is measured by the Hubble constant, roughly 70 kilometers per second per megaparsec. This means for every 3.3 million light-years of distance, galaxies move apart at 70 kilometers per second. In a black hole universe model, expansion is a critical puzzle.
Standard cosmology explains expansion as a result of the Big Bang, where space itself began stretching 13.8 billion years ago. Inside a black hole, expansion could arise differently. Some theories suggest that the new space-time region within a black hole undergoes a rapid stretching, mimicking cosmic expansion. This stretching could align with the universe's observed density, about 1 × 10⁻27th power kilograms per cubic meter, and its size, roughly 46.5 billion light-years across.
The Kerr model adds complexity to this picture. A rotating black hole's internal dynamics could influence the rate of expansion, potentially imprinting a rotational bias on the emerging universe. The fact that 2 out of every 3 spiral galaxies rotate in the same direction, as found in recent studies, supports this idea. This rotational coherence, combined with the universe's mass of 1.5 × 10⁻53rd power kilograms, strengthens the black hole hypothesis. These models are speculative, but testable. Astronomers can use telescopes to measure the universe's expansion rate more precisely, looking for signatures of a black hole's influence. Theoretical physicists are also exploring how a Kerr black hole's properties, like angular momentum, could shape a universe's evolution. These efforts bridge observation and theory, pushing us closer to understanding our cosmic origins. Testing whether our universe exists inside a black hole requires precise observations. The hypothesis hinges on evidence like cosmic rotation and density alignment. To confirm or refute it, astronomers use advanced tools to study the universe's structure and motion. These methods include galaxy surveys, gravitational wave detection, and cosmic microwave background analysis. Each approach offers unique insights, but faces significant challenges. The claim that 2 out of every 3 spiral galaxies rotate in the same direction needs broader confirmation. Current studies, based on a few hundred galaxies, are a small sample of the billions in the observable universe. Large-scale galaxy surveys, conducted with telescopes like the James Webb Telescope, can map the spins of thousands of galaxies. These surveys measure light patterns to determine rotational direction, revealing whether the universe has a net angular momentum. The challenge lies in scale and precision. Observing distant galaxies requires long exposure times, and dust clouds can obscure spin patterns. Surveys must also cover regions far beyond the Milky Way galaxy to avoid local biases. Future projects, like the Vera Rubin Observatory, aim to image millions of galaxies, providing data to test the rotational bias. This could strengthen or weaken the black hole universe model.
Gravitational waves, ripples in space-time caused by massive objects, offer another test. Detected by observatories like the Laser Interferometer Gravitational Wave Observatory, these waves reveal events like black hole mergers. If our universe formed inside a black hole, its space-time might carry subtle wave signatures from the parent black hole's spin. These signatures could appear as a background hum in gravitational wave data. Detecting such signals is difficult. Gravitational waves from cosmic events are faint, and distinguishing a background signal requires extreme sensitivity. Current detectors focus on nearby events, but next-generation observatories, like the planned Laser Interferometer Space Antenna, could probe deeper cosmic signals. These advancements may uncover clues about the universe's origin, supporting or challenging the black hole hypothesis.
The cosmic microwave background, or CMB, is the universe's oldest light, dating back to the Big Bang 13.8 billion years ago. It carries information about the universe's early structure. If the universe has a net rotation, this might appear as a slight twist in the CMB's temperature patterns. Satellites like the Planck Observatory have mapped the CMB in detail, but no clear rotational signal has been found yet. Analyzing the CMB for rotation is complex. The signal, if present, is likely very weak, buried in noise from other cosmic processes. New analysis techniques using artificial intelligence are being developed to search for subtle patterns. These efforts could reveal whether the universe's expansion, measured at 70 kilometers per second per megaparsec, aligns with a rotating black hole's dynamics. Each method faces limitations, but together they build a stronger case. The universe's mass, about 1.5 times 10 to the 53rd power kilograms, and density, 1 times 10 to the minus 27th power kilograms per cubic meter, already suggest a black hole-like structure. Confirming cosmic rotation or detecting unique space-time signals would bolster the hypothesis. For now, these observational challenges highlight the need for more data and innovative technology. The idea that our universe exists inside a black hole is bold, but it's one of many theories about cosmic origins. Cosmology offers several competing models, each attempting to explain the universe's structure, expansion, and features like its rotational bias. Comparing these alternatives to the black hole hypothesis helps us understand its strengths and weaknesses. Let's examine three prominent theories: the multiverse, cyclic cosmology, and inflationary cosmology.
The multiverse theory suggests our universe is one of many, each with its own laws of physics. These universes could exist in separate space-time regions, like bubbles in a vast cosmic foam. In some multiverse models, black holes in one universe could spawn new universes, aligning with the black hole hypothesis. Our universe, with a mass of 1.5 times 10 to the 53rd power kilograms, might be one such bubble, born inside a black hole's event horizon. The multiverse explains the universe's fine-tuned properties, like its density of 1 times 10 to the minus 27th power kilograms per cubic meter. However, it struggles with testability. No direct evidence of other universes exists, and detecting them may be impossible due to their separation from our space-time. The black hole hypothesis, by contrast, ties to observable data, like galactic rotation, where 2 out of every 3 spiral galaxies share a spin direction. Cyclic cosmology proposes that the universe undergoes repeated cycles of expansion and contraction. Each cycle begins with a Big Bang and ends with a collapse, followed by a new Big Bang. This model could explain the universe's expansion, measured at 70 kilometers per second per megaparsec, without requiring a black hole. A rotating universe might arise if angular momentum persists across cycles, passed from one phase to the next. Cyclic models face challenges in explaining the universe's current acceleration, driven by dark energy. Observations show galaxies moving apart faster over time, which conflicts with the collapse phase of cyclic cosmology. The black hole hypothesis avoids this issue, as its internal space-time could stretch indefinitely, mimicking our observed expansion. The Kerr black hole's spin discussed earlier also better accounts for the rotational bias in galaxy spins. The standard model of cosmology includes inflation,
a rapid expansion in the universe's first moments, 13.8 billion years ago. Inflation explains why the universe appears flat and uniform, with galaxies spread evenly. It assumes a Big Bang origin, followed by a brief, explosive growth. This model doesn't naturally predict a net rotation, making the observed galactic spin pattern, where 2 out of every 3 galaxies align, harder to explain. The black hole hypothesis offers an alternative. A rotating Kerr black hole could imprint angular momentum on its internal universe, causing coordinated galaxy spins. Inflationary models rely on a hypothetical field called the inflaton, which lacks direct evidence. The black hole model, while speculative, leverages known physics, like general relativity, and aligns with the universe's size, roughly 46.5 billion light-years across. Each theory has merits, but the black hole hypothesis stands out for its connection to observable data, like rotation and density. Multiverse and cyclic models are less testable, while inflation struggles with rotation evidence. Future observations using tools like the James Webb Telescope could tip the scales. For now, the black hole universe remains a compelling contender in the quest to understand our cosmic roots.